Hello, welcome back. Today we are going to see the convolutional layer. The convolutional layer was created and based on our brain and how we see the images. It is a really abstract concept, so you may not understand how and why we are using this kind of layer, but I can tell you that it's really efficient and optimized and allows us to recognize different kind of objects, and in image recognition is the most useful kind of layer. So the convolutional layer works similar as the pooling layer. If we have this kind of image with some rows and columns, and we need to operate it, we need to make a minor matrix like this size maybe, and now we can start operating it. First we have a filter that will have the same size as our minor matrix, and to operate it we use the Hadamard product, and then we sum the results into one output. So how it works: we multiply the first element by the first element of the filter, the second element by the second element, and once we have multiplied, I will write it W Y X Y. So the result will be, the output will be the sum of the multiplications of each value. So I think this is really easy, the operation. And why is it so important to us, this operation? Because it allows us to recognize different shapes and figures or edges. So imagine you have a filter that this kind of filter that we have a -1, -1, 0, 0, 0, 1, 1 and 1. If you have an image like that will be a 7, and if you apply this kind of filter, it will output a high value in this zone and a lower value on this zone and nothing on the other side. So what does it mean? That this kind of filter, for example, recognizes the horizontal edge. So is a edge filter and works really well, and also compress our image and reduce the size of it. The convolutional layer, as we have seen in the pooling layers, has hyperparameters and also has parameters. In the pooling layers we have seen that we didn't have parameters. The parameters will be the filter, our filter, this filter, and the hyperparameters will be the stride that we have seen in the pooling layer, the padding. We also have padding in this layer, and I think that that's all. We don't have too much hyperparameters here to see. So another hyperparameter that we can set is the filter size. The filter size in X and the filter size in Y. So these hyperparameters will be set before the compiling time, and we didn't see that in the pooling layer, but the size of our output would be a kind of formula that is not really difficult. I haven't said that before, but in convolutional layers we have seen the operation with only 2 dimensions, but we often see that we have more than 2 dimensions, like 3. We see the 3-dimensional inputs when we have an image with colors, with RGB colors, because we have one dimension that would be the red color, other dimension that would be the green, and other the blue color. So we can have 3 dimensions in 3-dimensional inputs in our neural network. And how we compute this kind of layer, this kind of input? Well, we need to have a filter that is also 3-dimensional, because otherwise you cannot operate a 3-dimensional image. So you have to care about this kind of images, and you can also transform this image into 2-dimensional image, but you will lose some information. So usually on convolutional neural networks we define we conserve our 3 channels. The red, green, and blue are also called channels. Okay, now we can start coding the convolutional neural network. The first thing that we have to do is include some files. The first one, the vector, the eigen, and you need also to create a convolution file that you can download on the internet in the GitHub project that I've made. I have this file is not mine. It's based on this website link, and computes the convolution using a memory efficient algorithm and works really well. So now we can I have defined some variables, and you could now define the internal convolution. Here we will say store some dimensions of convolution, the filter data that we are going to use, the derivative of the filter data, and now we can define the bias. I haven't mentioned that before, but the bias works when we have the set. When we are going to calculate the set, we need to add the bias. It is really easy. The derivative of the bias, and now we can define the set, the A, and its derivative, M, derivative of the input. So now we can define the constructor of the class. We have to define the size of the input width. We also need to define the height. The number of channels that you would input, the output number of channels, the window width, and the window height. As we have done in the pooling layer, we have to define the constructor of the layer that we are going to override. Width minus windows plus windows width plus 1 multiplied by the input height minus the window height plus 1. Here we have the dimensions of our window, multiplied by the output channel. I think that's all. No. Yep. Now we initialize the derivative of the set and the A. Channels in height, in width, window height, and window width. That's all. Now we need to override some functions that we have initialized in the virtual class. Oh, we have not included the random. Yep, we have included. Okay. We also need to override the forward function. This is really repetitive because the pooling layer and the convolutional works really similar. Now we define the getter of the output, MA, and the back prop. Some people backpropagates the filters of the parameters that we define in our filters to convolve the layer, and others use a constant filter that you set before you calculate the convolutional layer. In this case we haven't got filters defined yet, so we are going to backpropagate them to enable to learn them, and we are going to create the hours. Backprop the data, and we return the derivative of the input. Okay, that's all. So now we need to define the initialize function. The filter data size and dot in channels multiplied by m. You may notice that I have used the variable mdim, the convolutional dimensionals, to store all the values that we have set. So now we have to call mdim to get our parameters. Mdim dot in channels dot out channels multiplied by dot filter rows mdim dot filter calls. That would be the size of our filter and we may have more than one filter. You have to not to care about it. Filter data dot. Now we resize it, the size, and the derivative of the filters also need to be redefined. Now we need to initialize, to set our filter data with the normal distribution function that we defined in a previous video. We pass the filter data, the size, the random generator, the mu, and the sigma. Oops. And we also need to resize the bias and the derivative of the bias. And we now initialize set normal random, the bias data, the number of bias values, output channel, the random generator, mu, and sigma. Yeah, that's. We need to order it. We can now start defining the feed forward function in the convolutional layer. the first thing that we need to do is to resize the set. We go to our convol function that, if you have noticed, we have two of them, the full convolution operation and the valid convolution. If you if you go to the website that I have recommended you, you may see that there are three types of modes to convolve our neural network. The valid is the same mode, and the full In the neural network we have implemented the full and the valid. So if you look to the theory, you would understand why what are the difference and why we have used the valid, the full, and when we have to choose some of them. So that's all. In this tutorial we are going to use the valid, but you can change it if you want. Prep layer data dot data true. Number of observations, and filter data dot data So now we have defined the convolution operator. So and we now need to add the bias in channel. Start row. .com. The number of rows multiplied by the number of calls. And now we are going to loop through our output channels. And the start row plus equal the channel element. This is the number of elements in a row, so we are going to loop through each row in this set is gonna be the block function, the start row 0, the number of elements in a row, the number of observations, and dot. We are now need to apply the bias to the result. Bias dot y, and we repeat this process every single channel. So now we have finished our feedforward function, and the last thing that we have to do is to define the A outside and the number of observations, activate mset and ma. Oh, I forgotten something. The first thing that we have to do is to define our activation function in a template. Activation. Okay. Now should be all. So I think that's all for now. Thank you for watching it, and sorry, we need to add the update function. I forgotten. Update. We call to the optimizer opt const aligned map back, the derivative of the filter or the weight. You can call them as you want. Dot data and f the data dot size. Const aligned map back, derivative of the bias dv dot data and dv dot size. And we also create an aligned map vector that will modify filter data def data dot size aligned map back. Oh, sorry. dv dot data Okay, now we have created our variables to loop through it, and we call to the update of the optimizer. Update w v. We optimize the bias and the weights. So that's all for now. Thank you for watching it, and see you in the next tutorial in which we are going to define the activation function of our neural network.